Okay, never mind. So here, that is what we have, and I would like to quickly find the direction in which this buoyancy force is acting on. Okay, the direction in which this buoyancy force is acting on. Okay, now we will quickly go through the calculations. Okay, and we'll take moments about a point. Let's just say D over here. Okay, let's specify some distances. This distance will be y1. Okay, this distance will be the same as this distance over here. Okay, and the weights, let's just label it as y2. Okay, and then the buoyancy force. Okay, right now again we are looking at the parallel pipe is yc. Okay, so the key is to find yc. Basically, we are again taking moments about point D. Okay, taking moments about point D, knowing that F3 and F4 will cancel out each other. So FB is going down, weight is going down, F1 is going down. Okay, so F1 multiplied by y1 plus FB multiplied by the YC, which is the distance, or basically the centroid of the buoyancy force. Later we will know what that is. Plus Y2 multiplied by the weight is equals to Y1 and F2. Okay, knowing that F1 and F2 are the same distance away from D. Okay, so that's Y1. Okay, now rearranging, and I would just like to keep the FB on one side. Okay, I will have Y1, okay, F2, take away F1, okay, correct? And after that, I will subtract y2, take away weight. Okay, we'll introduce two new volumes right now because we really need to, in order for us to resolve the equations. The first one you've seen. So the volume dash is the volume of the object. Or another word for it is the volume of the liquid displaced. Okay, now we got a VT, which is the total volume of parallel pipe. Okay? Remember, total volume. So now it's just basically the whole volume like so. This again, I say, is for convenience of resolving the equations, which we will see very soon. Okay, so this is what we have. Now y1, okay, so F2 take away F1. Just now I erased the equation, okay, but it's basically specific weight. H2 take away H1 times the area A. Okay, H2 take away H1, okay, basically is the height times the area A is basically the same as the total volume, correct? Okay, now we will need the Y2 multiplied by the weight of the parallel pipe, okay, which is basically, again, the specific weight, but this time we are taking the total volume, subtract by the volume displaced, okay? Again, W is the weight of the parallel pipe, or the water, okay, less the volume displaced. So basically the shaded volume over here. It's basically the total volume subtract the volume of the fluid displaced multiplied by the specific weight. That will give us the weight multiplied by y2, which is over here. So we got this equation, we got this equation over here. Okay, let me just have a quick check. Okay, that seems to be correct. Though one last correction is that we will just rewrite this as the buoyancy force, right? So it's the volume displaced multiplied by the specific weight, and so we can cancel, okay? So this is our final equation. Okay, bear with me, I'm almost done. Y2, VT, take away V dash. Okay, this is our final equation over here. Remember, we are finding, sorry, this is not, we got a YC over here. Yeah, we are finding YC. Our main concern is finding YC, the Y coordinate along the Y axis, okay, of the buoyancy force. The y-axis is like that, x-axis, and the z-axis like that. Okay, now this one, this term, this whole thing here is classified as the first, it's classified as the first moment, is classified as the first moment of displaced volume about the xz plane. Okay, this is classified as the first moment of volume about the xz plane. What is the xz plane? The xz plane is the plane over here like that. Okay, and that will just simply give us, okay, the y coordinate, because it's about the xz plane, the volume, that will give us the y coordinate of the displaced volume. The centroid, or in other words, the centroid of the displaced volume, okay? So actually it just equals to, like this, let's just say C0, where C0 is the centroid of displaced volume, okay? Or more specifically, the y coordinate of the centroid of the displaced volume. Okay, so that will, if we do the same calculations, okay, we will soon find out, and remember, this is the the YC over here is along the Y distance, okay, the location along the Y axis in which the FB is acting, okay. So we found out that this YC is gonna be the same as Y naught, where Y naught now becomes the centroid of the displaced volume. So, I mean, if we were to just simply write it out like that, okay, and XC is equals to X naught, okay, using these calculations, taking the moments, we conclude that the buoyant force, okay, passes through the centroid of displaced volume. And there we go. That is the location of the buoyant force, okay, which passes through the centroid of the displaced volume. Like we all expected. But to derive it, we must take moments about an axis. Now, last thing, assuming, and this is very important, assuming specific weight is constant, okay. Assuming specific weight is constant. Now, if specific weight is not constant, it is not the centroid of the displaced volume. Instead, it is the center of gravity of the displaced volume. Okay, center of gravity. Why is that so? Because basically, at each point of the displaced volume, there's a different specific weight. So that is what the center of gravity means. We will sum up the different points of the displaced volume, taking into account the change in the weight. Likewise, the change in the specific weight to find the center of gravity. Okay, so assuming the specific weight is constant, buoyant force, centroid, very easy. Assuming it's not constant, center of gravity of displaced volume. Okay, and there you go, my friends. A mathematical treatment in finding Archimedes Principle. Okay, now you can tell all your friends. The second part of the video is about too cheap to understand. Oh, sorry. That's a Singapore term. Too difficult to understand. I hope the first half was worth your time. Okay, thanks.